Right, I'd like to do a little more today on the strong nuclear force and look at different aspects of it. Remember last time we saw that the strong force binds quarks together to create, well, there's two different kinds of particles it can create. So far we've just talked about the baryons, but also we'll talk today about the mesons. Okay, and remember that baryons are spin 1/2 particles. Like the electron, and so that means that they obey the Pauli exclusion principle. In other words, the composite wave function can be thought of as, this is 1 over root 2 of psi A of 1, psi B of 2 minus psi B of 1, psi A of 2, such that if the quantum numbers A and B are equal, then the psi wave function is equal to 0 in a two-particle system. And so this then causes the wave function to cancel out if the quantum numbers are the same. Then psi is equal to 0. And A and B are quantum numbers. So if the set of quantum numbers that corresponds to a particular state, and before we were talking about electron state, but here we can also be talking about nuclear states as well. These could be states of fermions that are quarks. Okay? And so baryon is a spin 1/2 particle, and that's called a fermion. And that is what obeys the exclusion principle. Now, on the other hand, we're going to be talking today about mesons. This is a spin 1 particle. Or in general, this would be some integer multiple of 1. And so mesons then don't obey the exclusion principle. Their psi is 1 over root 2 for a two-particle system, psi A of 1, psi B of 2, plus psi B of 1, psi A of 2. And you can also write this for multi-particle systems as well, but this is a simple version of it, so that if A equals B, the psi is not 0. And what this means is that you can have any number of particles in the same quantum state. So examples then of spin 1 or spin 0, or it could be spin 2 particles, anything that has an integer spin. Examples would be the helium atom. So in the helium atom, you can have a basically a group wave function of all the helium atoms in the same quantum state, and it can act like a single object that's basically resonating with itself. And so an entire mixture of liquid helium then can have this property that every helium atom in this system can be in the same quantum state. They don't exclude each other and fill up available energy levels, as is the case with a spin 1/2 particle. Photons are another example. And also phonons. which are particles that can exist in some aspects of solid state physics. These are examples of particles that can basically superimpose on each other. Have what's called a Bose-Einstein condensate, which has some very exotic properties associated with it, in which all of the atoms are in the same quantum state. And so we'll be talking more about mesons, which is a type of boson, in a little while. Okay, so let's go back over here, and with these introductory thoughts in mind, let's think in terms of some of the spin properties of quarks. We haven't talked about those yet. The quarks are spin 1/2 particles, which makes them fermions, just like the electron. And so if we are going to have several of these fermions in the nucleus, say 2 ups and a down, as would be the case for a proton, or 2 downs and an up for a neutron, then you would think that they would have to obey the Pauli exclusion principle, right? Because they would be very close to each other. The nucleus, we're on the order here of just a femtometer, which is 10 to the minus 15 meters. Okay, so they're essentially right on top of each other. And so according to at least the ideas as defined by spin 1/2 particles, they shouldn't be able to exist together like this because they're spin 1/2 particles. And for 3 quarks, you have different composite fermions that could have any kind of spin between 3/2, 1/2, -1/2, -3/2, and multiples of 1. Going, if they're all aligned, 1/2 plus 1/2 plus 1/2, so it'd be 1/2 plus 1/2 -1/2 goes plus 1/2. Or you could have 2 down spins and an up spin, -1/2, -1/2, plus 1/2, or they could all be down. Turns out that for baryons, they're spin 1/2. Okay, and so we have spin 1/2 particles in the nucleus that shouldn't be able to exist because of the exclusion principle that we talked about before. Remember, this is that same principle that allows for electrons to fill up different quantum states in an atom, but doesn't allow for 2 identical quantum numbers for any given electron. And so they basically, the wave function cancels itself out for that kind of thing. And so they started wondering about this when they were first proposing the idea of 3 quarks making up a baryon. Okay? And so this is what was the motivation for them coming up with color. They go, okay, well, if these are spin 1/2, then they should be canceling each other out unless there's some stronger force that can overcome the effects of the Pauli exclusion principle. So they go, well, since we have good reason to believe that there are 3 of these, then it makes sense that we would have 3 colors which could add up to 0, so that you would still have a colorless nucleon. But that would bind this thing together and overwhelm the effects of the Pauli exclusion principle. So that was the whole idea behind hypercharge. So long story short, hypercharge, attraction, overcome the Pauli exclusion principle. In other words, this is a tendency for the system, and you could also write this for a 3-nucleon system too. I just am doing this with 2 because the mathematical expression is less complicated, but it's easy enough to do this for 3 as well, and you could do that just by writing the determinant of something that would have psi A1, psi B2, psi C3, and you'd have 3 rows, and then you would just write the determinant of that, and that would give you the antisymmetric wave function for a 3-particle system. But that's not necessary here. We're just kind of looking at the basic features. And so this is the reason why hypercharge can overcome the exclusion principle. But remember that 0 hypercharge is equal to an equal amount of red, green, and blue. Okay, so if we want the nucleon, the proton or the neutron, which again is also called a baryon. This is a baryon, this proton, and a neutron. These are baryons which have 3 quarks. But it's also a fermion because it's half integral spin. And it's also a hadron, which is something that has quarks in it that's influenced by the strong force. So this hadron is just a more general classification that includes baryons and mesons, as we mentioned before. But it's also a fermion. And so we can see then that to satisfy the concept that the total nucleon have 0 hypercharge, we are forced to have 3 quarks because there are 3 colors. And so this is the only way to make a nucleon that has 0 total hypercharge. If you just had green and red, that wouldn't equal 0 because you have to add the blue in so that the total hypercharge is equal to 0. You couldn't have 4 because then you'd have to have red, green, and blue and then something else, either red, green, or blue, which would give the nucleon some non-zero hypercharge. Similarly with 5 particles. Couldn't do it with 5 either because then you'd have, say, red, green, and blue, and then red and green, but not blues. So, but you could have it with 6. Okay? And it turns out that you can also have it with 2, but they have to be the anti-charge of each other. So you could have, say, a blue and an anti-blue for a 2-quark system. And it turns out that that's the case with mesons. But this shows us then why this is consistent then with the spin 1/2 particle for the proton. If each of the individual quarks is spin 1/2, then that's one of the possibilities in which 2 of the spins are up and 1 of the spins is down, which we could think of as being consistent, say, with maybe the up quarks being spin up and the down quark being spin down, something like that. And then with a neutron, it would have the opposite spin because these would be 2 spin downs. This would be a spin up. So it turns out that the spins, plus and minus 1/2 for the neutron and the proton, are oppositely directed, but is consistent with the idea of a fermion. Okay? And so this is kind of the motivation for how scientists first started thinking in terms of the introduction of this new kind of charge and the kinds of symmetries and numbers of quarks that could fit into a particle like a baryon in order to produce either a proton or a neutron. Okay, and so we already talked about how the gluons, when they're exchanged back and forth, can bind this system together. What I want to do next is take a look at mesons and the second aspect of the strong nuclear force. And typically, the kind of mesons that we're looking at here are first generation mesons, which would be either the pi 0, the pi plus, or the pi minus. And these mesons are exchange particles that can mediate the second aspect of the strong nuclear force. And so what is the second aspect of the strong nuclear force? Remember, the first aspect was holding together the nucleons, the protons and neutrons. So it was a force that held the quarks together within a nucleon that had to have 3 elements to it so that it has 0 total hypercharge and so that the spins could add up to 1/2 so that it could be a fermion. Okay, but with the mesons then, this is the aspect of the strong nuclear force that binds together protons and neutrons in the nucleus. And so these mesons then spin 1 particles. They only have 2 quarks. Okay, so you say, well, if you need 3 quarks to have a colorless system, then how on earth can you have 2 quarks and still have a colorless system? And the answer is, in this case, the 2 colors are the color and the anticolor. So in other words, this would be like green and anti-green, or blue and anti-blue, or red and anti-red. Or it could be a combination of all 3 of those. Okay? But it has to add up to 0 total hypercharge by having equal amounts of a color and its anticolor. And so, as I said before, this is the second aspect of the strong nuclear force. Because the first aspect is first you've got to hold the quarks together to create a nucleon, one of these baryons, like a proton or a neutron. Okay? But then you've got to hold the protons and neutrons together in the nucleus too. And it turns out that is an aspect of the strong nuclear force. Let's see how that's done. Well, a pi plus, if it's first generation, it will only be made out of up and down quarks. And we're talking mostly now, at least to begin with, in terms of first generation particles, because those are the ones that are most common in the universe. They're the least energetic, and so the heavier, higher generational particles are similar to these, although they just have more mass, but they've got the same properties of charge and spin, angular momentum, as the lower generation ones do. Okay, so here if we want a +1 charge and we only have 2 quarks to work with, then let's try an up, because that's +2/3, and an anti-down. Because a down is -1/3, and so an anti-down is +1/3. So that gives us a spin of +1, or I'm sorry, a charge of +1. Also give us a spin of 1 if these two, remember that quarks are spin 1/2 particles, and so if you have an even number of them, you're going to have an integer multiple of an integer, like 1. Okay, and so it also has a integer spin, which makes it a boson. Okay, and so we also have a pi minus, so what would that be? Well, we want it to be -1 total charge, and so how about an anti-down? That'd be -2/3, or I'm sorry, anti-up, and a down. That'd be -1/3. So then the charge would be -1. Okay, so these particles can exist on their own and are stable. They can also exist as virtual particles as well. And so if we were to, let's say, have an interaction in the nucleus between a proton and a neutron, we can write this in terms of what's sometimes called a Fineman diagram, in which the particle starts out, and let's do this with a neutron first, on the left, and a proton. And then the neutron comes in, and then it exchanges a particle with the proton. So we can imagine this direction here to be the forward direction in time. And the neutron and the proton then interact, and in the process of interacting, they're going to need to, well, the neutron here is going to change into a proton after it interacts, and the proton is going to change into a neutron. Okay, and so this is the basis then for this second aspect of the strong nuclear force, is that the neutron can interact with the proton, but in the process of doing that, the proton is going to change its identity. The proton's going to change into a neutron. The neutron's going to change into a proton. So you haven't changed the total number of protons or neutrons in the nucleus. But you can exchange a pi meson that will allow this to happen, and that exchange of the particle is what will initiate the strong force that'll hold these particles together. Okay, and so this is how the neutron can act like nuclear glue and help to hold it together with the protons. So remember before we were saying that here's our proton, here's our neutron in the nucleus, and they're like little short-range hooks that hold them together. Okay, this is the mechanism of the hook that I'm talking about here. This exchange of a virtual particle is the hook. Okay, and so here for the neutron then, we know that a neutron is 2 downs and an up, and a proton is 2 ups and a down. Okay, so what we're going to want to do here is exchange a pi minus. Why pi minus? Well, because a pi minus here is an anti-up down. Okay, so if the neutron is going to give up, let's say, a down quark, okay, and so it'll do that by taking one of these down quarks and delivering it over there. But in order to break loose, in order to get this free quark to escape, you've got to give it a lot of energy because there's a lot of force holding it in. We already talked about that force over here with the gluons, the nuclear glue. It's a lot of force to hold it in. So by the time you pulled on it so hard as to allow it to escape from the nucleus, you've added enough energy to create a quark-antiquark particle pair. So that's why you never get any free quarks in nature, is that the energy that's required to pull a quark loose is enough to create a quark-antiquark particle pair, so they'll pair back up again with the energy that's produced these new quarks. All right? So here then, you have a anti-up and a down. So one of the downs came from the neutron, and so then that energy produces an up anti-up virtual particle pair from the uncertainty principle. Okay, so this is a virtual particle in which the energy that's freeing the down quark that's borrowed from the vacuum is enough to make an up anti-up quark. And so then the anti-up goes in along with the down. Okay, and so if we do that, then what we're left with is two ups and a down, which is a proton. Okay? And so we've delivered this negative charge, and so then that ensures that the proton now has a positive charge because we've delivered a charge of -1 to this proton. That cancels out the charge on this proton, turns it into a neutron. The proton is two ups and a down, so the up and the anti-up cancel. The down comes in and takes its place so that you have two downs and an up. Okay, so this is the process then of binding, nuclear binding, that takes place when a neutron and a proton exchange a virtual pi meson. And in the process of doing that, the neutron and the proton switch identity. Okay, so this is the result then of the exchange of the virtual pi meson. Is first the particles change identity, and a binding force, strong binding force I should say here, way stronger than the electrostatic repulsion, is exerted. And so similarly, you can do this with a proton exchanging a positive pi meson with a neutron. So in this case, the proton is throwing a virtual particle at the neutron. And remember that our pi plus is an up anti-down. Okay, and here we have two ups and a down. Here we have two downs and an up. Okay, so if we take one of the ups and then we have a down anti-down that are produced by the uncertainty principle, the delta E delta T is producing this. Okay, but only over a sufficiently short distance so that it can pay back that energy before it runs out of time. So in other words, the pi meson is exchanged before it runs out of lifetime as a virtual particle. Okay, so we've got rid of an anti-down, that leaves behind a down, and we've gotten rid of an up. So what we've got left here then is a neutron, because now we've got two downs and an up. But then over here, this is a down and an anti-down cancel. So, and then we're delivering an up to the neutron, and the down is gone. So that's two ups and a down. And we've also delivered that charge of +1 to the neutron so that we've conserved charge. Okay, so we still have the same number of protons and neutrons in the nucleus, but the identities of them aren't something that needs to be conserved. And so it's okay to switch identities in the process of transferring a pi meson, either a positive or a negative one, to the other side. Now, this whole idea was speculated on in the 1940s. The idea was that if delta E delta T is approximately h bar, and delta E here is equal to somewhere on the order of mc squared, in order to produce the virtual pi meson, then the delta T can come from C delta T equals the range of the strong nuclear force, which is about 1 femtometer, or 10 to the minus 15 meters. Okay, so we can rewrite then delta T as delta X over C equals h bar, or you get mc squared equals h bar C over delta X. And doing that calculation, we found that the mc squared was about 200 MeV. Guess what? That is the energy of a virtual pi meson. Okay, so there you go. This is a verification of the idea that the range of the force, being about 10 to the minus 15 meters, is consistent then with an uncertainty principle particle that can be created that can live just long enough to exchange the particle before the particle decays back into the vacuum. Okay, and so then that creates the binding force, but it can't go any farther than this because the particle can't travel any faster than the speed of light, and so that would be a maximum distance that it could go with a typical lifespan. And so that's why the nucleus is so small. And also, as we mentioned before in a previous lecture, that also relates directly to h bar, because here, if h bar were a much bigger number, then that would change everything.